So this is lecture 9 in ordinary differential equations. We're talking about second order linear homogeneous equations. So this is in section 5.1 of chapter 5. After this, of course, we cover section 5.2, and the midterm exam in 3 weeks covers chapters 1 and 2 and sections 1 and 2 in chapter 5. And a second order linear homogeneous equation is an equation of the form y double prime, second derivative of y, plus some function p of x times y prime, plus a function q of x times y equals 0. So this is the general second order equation. And the linearity means the following, that if y1 and y2, let me call this equation star, so I don't have to keep writing it. If y1 and y2 are solutions of star, then every what is called a linear combination of y1 and y2. This means a function y, which you can write as some scalar multiple c1 times y1 and some scalar number c2 times y2, is also a solution. And we saw several examples of that. For example, if you take the equation y double prime plus y equals 0, one solution is y1 equals sine of x. Another solution is y2 equals cosine of x. And you can check, you differentiate each of these functions twice, you get the negative of what you started with. And so if you take y to be any linear combination of sine x and cosine x, this is also a solution. And so, for example, y equals 7 sine x minus 29 cosine x. It's a solution. You're choosing c1 equal to 7 and c2 equal to minus 29. Right? So that's what we mean by a linear combination of two functions. And any linear second order homogeneous equation has this property. If you have any two solutions, every linear combination of them is another solution. Okay, so that's one fundamental fact. But what's even more fundamental is that sometimes not only is every linear combination of y1 and y2 a solution, but if you choose y1 and y2 properly, every solution is a linear combination. So let me state this fact also. So again, we have our differential equation, y double prime plus p of x y prime plus q of x y equals 0. And we say a set of two solutions, y1 and y2 are solutions of this equation. And we say that y1, y2 is a fundamental set of solutions if every solution y of the equation is of the form y equals c1 y1 plus c2 y2. So this doesn't say that a fundamental set of solutions exists, but it is a definition of a fundamental set of solutions. And it obviously is something very nice because differential equations will always have infinitely many solutions. but you can find all of them if you can only find a set of two solutions that are fundamental. Right? So that's the idea. And it will turn out there's a simple criterion for a set of solutions to be fundamental. This is a theorem. So solutions y1 and y2, this set of solutions is a fundamental set if and only if, that's what this double-headed arrow means, if and only if y2 is not some constant times 1 for some number scalar c. So if you have any two solutions and one is not simply a constant multiple of the other, then that pair of solutions is a fundamental set. All right, so that's a theorem we'll prove. But for example, the set of functions sine x, cosine x is a fundamental set for the second order equation y double prime plus y equals 0, because sine of x is not some constant times cosine of x. This equation isn't true for all x. It's not that this trig function and this trig function, one is a scalar multiple of the other. So this is not true. So sine and cosine do form a fundamental set for this differential equation. Okay. So this is a basic concept that's very important to internalize, to master. And there's a name for a pair of functions that have this property, and it is the following. So functions y1 and y2 are called linearly independent if y2 is not a scalar multiple of y1. So another way of stating this theorem, right? This was the theorem. y1, y2 is a fundamental set if y2 is not a scalar multiple of y1. So this is the same as saying if and only if y1 and y2 are linearly independent. Linearly independent functions. Okay. And in fact, we don't prove everything in this course because a lot of the theorems require more mathematics than is a prerequisite for taking ordinary differential equations. But this is a theorem we will prove. Okay. The basic existence and uniqueness theorem for these equations is the following. So this is the existence and uniqueness theorem. This is for, again, second order linear homogeneous differential equations. If P of x and Q of x, those are the two functions that define the differential equation, are continuous on an open interval AB, and if x naught is in this open interval, so x naught is strictly between A and B, then for all scalars, numbers k0 and k1, there exists a unique function y that solves my differential equation, and that's always my differential equation, and satisfies the initial conditions that y evaluated at x0 is k0, and the derivative of y at x0 is k1. So this is the basic theorem in our subject for linear homogeneous second order equations. So long as P and Q are continuous on an interval AB, there exists a unique function y on this entire interval, not a piece of it, but on the whole interval, that satisfies this equation and satisfies any initial condition. Right? So this is really key. And you need to know this. When you take the midterm exam, it's not an open book exam, and you can't use a calculator or a computer. You just have to solve the problems with pencil and paper, which is the only way to know and to show that you have mastered the subject. Okay. So this is the existence and uniqueness theorem. And what I wanted to start to talk about, or continue to talk about, because we started yesterday, is this theorem that says you have a fundamental set of solutions for your differential equation if and only if the two solutions in your set are linearly independent functions, right? That is the key thing. And a principal tool in this subject and used to prove our theorem is something called the Ronskian of two functions. So let's just recall something about a 2x2 determinant. If you have a 2x2 matrix that is just an array of four numbers, A, B, C, D, and you put them in these sort of absolute value signs, this is just the number AD minus BC. So 7, 3 minus 2, 8 is 7 times 8 minus 3 times minus 2 is 56 plus 6 is 62. That's a determinant. And what is called the Ronskian with a W, the Ronskian of functions y1 and y2 is this number W. It's a function of x. No, let me write it in two ways. So W is the determinant of a 2x2 determinant. The first row is y1 and y2. The second row are the derivatives of y1 and y2. So this means y1, y2 prime minus y1 prime, y2. Or as a function of x, W of x is y1 of x, y2 prime of x minus y1 prime of x, y2 of x, right? This is a function of x. So for example, if y1 is equal to sine x and y2 is cosine x, then the Ronskian, I can write this as the Ronskian of y1 and y2, or the Ronskian of sine x cosine x, that's the determinant of what? You write the two functions in the first row, sine x, cosine x, and their derivatives in the second row. So when you evaluate this, you get minus sine squared x minus cosine squared x, which is minus sine squared x plus cosine squared x. So that's minus 1. So for these two functions, the Ronskian is just identically equal to minus 1 for all x. If we looked at, for example, the differential equation y double prime minus y equals 0, two solutions of this differential equation are y1 equals e to the x and y2 equals e to the minus x. So what is the Ronskian of these two functions? You write them in the first row, e to the x, e to the minus x. In the second row, you write their derivatives. The derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x. Oh, this is funny. So when you compute this, the determinant, you get e to the x times minus e to the minus x minus e to the x, e to the minus x. That's minus 1 minus 1. This is minus 2. Right? If you take the functions y1 equal x squared and y2 equal 1 over x squared, what is the Ronskian? And so that's the Ronskian of the functions x squared and x to the minus 2. That's 1 over x squared. So that's the determinant. The first row is x squared, x to the minus 2. In the second row, we write the derivatives. The derivative of x squared is 2x. The derivative of x to the minus 2 is minus 2x to the minus 3. When you calculate the derivative, you get x squared times minus 2x to the minus 3 minus 2x times x to the minus 2. So this is minus 2 x to the minus 1 minus 2x to the minus 1. That's minus 4 x to the minus 1, or minus 4 over x. So for these two functions, this is the Ronskian. So maybe take a minute and maybe do this calculation yourself, or maybe to make it more interesting. Suppose you take the functions x squared and x cubed. Calculate the Ronskian. Calculate the Ronskian of x squared and x cubed. So this is a 2 by 2 determinant. First row is x squared, x cubed. Second row is 2x, 3x squared. When you compute this, you get x squared times 3x squared, 3x to the 4th, minus 2x times x cubed, which is minus 2x to the 4th. So this is x to the 4th. That's the Ronskian. All right. Any questions about that? Okay. So what is the connection between fundamental sets of solutions of this differential equation and the Ronskian? Right? I mean, there has to be a reason why we're talking about this now. So we have so suppose, let's look at some conditions for a set of functions to be fundamental. Suppose y1, y2 is a fundamental set of solutions for the equation y double prime plus p of x y prime plus q of x y equals 0. Where p of x and q of x are continuous on some open interval from A to B. So what does that mean? That means that for all x naught in the interval, open interval from A to B, and all scalars, all numbers, k naught and k1, there exists a unique solution y of the differential equation that satisfies the initial condition y at x naught equals k naught, y of x1 equals k1. So if y1 and y2 is a fundamental set of solutions for this differential equation, then there exists scalars, numbers, C1 and C2, such that y is equal to C1y1 plus C2y2. So y is a solution of the differential equation that satisfies this initial condition. Y at x naught is k naught. The derivative of y at x naught is k1. So let me just write down exactly what that means. It means that y at x naught, which is C1 y1 of x naught, plus C2 y2 of x naught equals k naught, and y prime of x naught, which is C1 y1 prime of x naught, plus C2 y2 prime of x naught equals k1, right? That is, for all choices of numbers, k naught and k1, we can find C1 and C2 that solve these. What are these? These are two linear equations and two unknowns that solve these two linear equations, right? These are linear equations where the unknowns are C1 and C2. So you can solve these equations. Let's actually solve them. So let's solve. So if you know Kramer's rule, you can just write down the solution in one step. Or we can just solve it by eliminating, for example, C2. So let's multiply the first equation by y2 prime at x naught. You get C1, y1 of x naught, y2 prime of x naught, plus C2, y2 of x naught, y2 prime of x naught, equals k naught, y2 prime of x naught. I just took the first equation and multiplied by y2 prime of x naught. Then we take the second equation and multiply by y2 of x naught. I get C1, y1 prime of x naught, y2 of x naught, plus C2, y2 of x naught, y2 prime of x naught, equals K1, y2 of x naught. So these two terms are the same. If I subtract these equations, this cancels. So I get C1 times y1 of x naught, y2 prime of x naught, minus y1 prime of x naught, y2 of x naught, equals this right-hand side, k naught y2 prime of x naught minus k1 y2 of x naught. So if I can express y as a linear combination of y1 and y2, then in particular, I can solve these two linear equations. So when I eliminate C2, I get this equation. Let me eliminate C1. To eliminate C1, again, this is just high school algebra. You multiply the first equation by y1 prime of x naught. You get C1, y1 of x naught, y1 prime of x naught, plus C2, y1 prime of x naught, y2 of x naught, equals k naught, y1 prime of x naught. Then we multiply the second equation by y1 of x naught. I get C1, y1 of x naught, y1 prime of x naught, plus C2, y1 of x naught, y2 prime of x naught, equals K1, y1 of x naught. And again, if I look at these two equations, this term equals this term. So if I subtract, they cancel. So let me subtract the first equation from the second equation, this equation minus this. I get C2, y1 of x naught, y2 prime of x naught. Oops. Let's see, this was, let's make sure I do my arithmetic right. My writing is so bad. This is y1 of x naught, y2 prime of x naught minus y1 prime of x naught, y2 of x naught equals k1 y1 of x naught minus k naught y1 prime of x naught. So C1 and C2 solve these equations. Now, this expression in the square brackets here and here, here and here, they're the same. If that's equal to 0, you can't solve these equations unless these right-hand sides happen to be 0 for all choices of K0 and K1. And the only way these are 0 for all choices of K0 and K1 is if y2 of x0, y2 prime of x0 are 0, y1 prime of x0, y1 of x0 is 0. The only way that can happen is if y1 equals y2 is the function which is identically 0. So if y is not the 0 function, then the only way you can solve these equations is if this is non-zero. And this is exactly the Ronskian. So what I have in my square brackets y1 of x naught, y2 prime of x naught minus y1 prime of x naught, y2 of x naught. That's this expression in the square brackets. That has to be different from 0, but this is exactly the Ronskian of y1 and y2 at x naught, right? This is exactly the determinant of y1 of x naught, y2 prime of x naught, y1 prime of x naught, y2 of x naught. This is exactly this determinant. That's the Ronskian. So what I just showed is, so this proves the following. If y1 and y2 is a fundamental solution of my differential equation, then the Ronskian of y1 and y2 is not equal to 0 for all x naught in the interval from a to b. Right. So if you have a fundamental pair of solutions, a fundamental set of solutions, the Ronskian is never 0. Now, there is a very pretty formula to express the Ronskian in terms of the differential equation. So let's state that result. So in the text, this is Theorem 5.1.4. So again, P and Q are functions which are continuous on an open interval from A to B. And y1 and y2 are functions that are solutions of my differential equation, y double prime plus p of xy prime plus q of xy equals 0. Suppose we let W be the Ronskian of y1 and y2, that's y1, y2 prime, minus y1 prime, y2. And let x naught be any point in the open interval from A to B. So this symbol, which looks like a Greek epsilon, is just mathematical notation for in, or x naught is an element in the set or the open interval from A to B. Right? So there's a theorem, there's a formula which is called Obel's formula, which says the following. you can write the Ronskian as, so the Ronskian is some function of x. It's the Ronskian evaluated at x naught times e to the minus the integral from x naught to x of p of t dt. So the formula only depends on the function p in the differential equation, but of course y1 and y2 depend on p and q. So how do we prove this? Oh, and either w of x equals 0 for all x in the interval from a to b, or wx is different from 0 for all x in the interval from a to b. Right? So this Ronskian, it's either identically 0 or it's never 0. So in particular, if it has 1 0, it's 0 everywhere. Right? So let's prove this theorem. And what can we say? So we know that, so this is proof. y1 and y2 are solutions of this differential equation. So we know that y1 double prime plus p of x y1 prime plus q of x y1 is 0, and y2 double prime plus p of x y2 prime plus q of x y2 is also equal to 0. So we have these two facts. And the Ronskian is the function y1 y2 prime minus y1 prime y2. So let's differentiate w. When you differentiate w prime by the product rule, that's equal to y1 prime y2 plus y1 y2 double prime. That's the derivative of the first term, minus the derivative of the second term, which is y1 double prime y2 minus y1 prime y2 prime. Oops. This should have been, I differentiate y1 prime y2 prime plus y1 y2 double prime. That's correct. It's plus, right? Minus the derivative of this, that's y1 double prime y2 plus y1 prime y2 prime. And this term and this term cancel. So this is just equal to y1 double prime, y1, y2 double prime minus y1 double prime, y2. And y2 double prime and y1 double prime can be written in terms of p and q and the functions in their first derivatives. So let me just write this over here. So w prime is equal to y1, and y2 double prime is equal to minus p y1 prime minus qy1 minus y1 double prime, sorry, y2 double prime. This was minus py2 minus qy2 minus y1 double prime. So from this equation, that's equal to minus py1 prime minus qy1 times y2. Let's see what this is. This is minus P y1, y2 prime minus Q y1, y2 plus P y1 prime y2 plus Q y1, y2. QY1, Y2 minus QY1, 2, they cancel. And I'm left with minus P Y1, Y2 prime minus Y1 prime, Y2. And this is exactly W, minus P times W. Right. So sorry, that wasn't visible, but there it is. So this function W satisfies the differential equation W prime is minus P times W, or W prime over W is minus P. Or if you integrate, the log of W is equal to minus the integral of P of t dt plus a constant. I can make this from x naught to x. All right, that's the antiderivative of minus P of x. So if I exponentiate, I get W is equal to e to the c, e to the minus the integral from x naught to x, P of t dt. And at x naught, you get this. So W is equal to W at x naught, e to the minus the integral from x naught to x, P of t dt. So let me just make one comment about this. So W satisfies this differential equation. So this only makes sense when W is either always positive or always negative. You can't divide by 0. So if W is positive, then well, we get this. I mean, this is exactly what it is. If you evaluate this at x naught, you get W of x naught. And if you look at this formula, an exponential is never 0. So what this formula tells us is, it tells us two things. First, it gives us an integral expression for W, for the Ronskian. And second, because this term is never positive, this says that if W at a point x naught is 0, W is 0 everywhere. And if W is non-zero somewhere, then it's non-zero everywhere. And that is exactly what we needed to prove here. Yeah. So that's the proof of theorem 5.1.4. And so that's a step in the direction of what we want to show, which is that a pair of solutions forms a fundamental set if and only if they are linearly independent. So let me write that down again. This is Theorem 5.1.3. Again, we have our differential equation. And the theorem says that two solutions, y1 and y2, are a fundamental set if and only if the two functions are linearly independent. That means one is not a scalar multiple of the other. So one step in this is that this was Theorem 5.1.4. The Ronskian of two functions is either 0 for all x or no x. Right? So either the Ronskian is identically 0 or it is always non-zero. And so the last thing I want to show, so this is Theorem 5.1.5. Again, for our differential equation, y double prime plus py prime plus qy equals 0. That y1, y2 are linearly independent if and only if the Ronskian is not 0. So I showed that if the Ronskian of two functions is of two solutions is non-zero, then it forms a fundamental set. So there's a connection between a fundamental set of solutions of this differential equation and the Ronskian being non-zero. And now I want to show that to say that the Ronskian is non-zero is equivalent to showing that our functions are linearly independent. So let's go through the proof of this, which is done very nicely in the text. And maybe I'll start a fresh piece of paper for that because it's going to take up some space. So we get the differential equation y double prime plus p of x y prime plus q of x y equals 0. And we have solutions y1 and y2 of my differential equation. And the Ronskian, as always, is y1, y2 prime minus y1 prime, y2. So let's suppose that the Ronskian is equal to 0 for some point x naught in the interval from A to B. So here we have the interval from A to B on the number line, and here's some point x naught. Now, suppose there's an interval, so let me write it the way the text does, that I be a subinterval from A to B. So maybe here is some subinterval I on which y1 is never zero. So you have to think about the following statement a little bit. So suppose on every subinterval, there's a point where y1 is zero. That means y1 has to be identically zero, because if it weren't identically zero, there will be some point where it's non-zero and then some interval around that where it's non-zero. So that I be a subinterval of AB on which y naught is different from zero for all points in the subinterval. Okay. So consider the function y2 divided by y1 on the subinterval. And let's differentiate this. Y2 over y1 by the quotient rule is the denominator squared, the derivative of the numerator times the denominator minus the denominator minus the numerator times the derivative of the denominator. This is exactly, the numerator is the Ronskian divided by y1 squared. If the Ronskian at x naught is zero, then the Ronskian at x is zero for all x, because we proved that if the Ronskian is non-zero at some point, it's zero at some point, it's zero everywhere. And in that case, the derivative y2 over y1 prime is zero, which means y2 over y1 is a constant, or y2 is constant times y1, or y1 and y2 are not linearly independent. They're linearly dependent. So if the Ronskian is zero somewhere, then the functions are linearly dependent. Right? So W next naught equal to zero implies the functions are not linearly independent. Suppose the Ronskian is never zero on the interval from A to B. That means y1 is not identically equal to zero. Because if y1 were 0, the Ronskian would be 0. And then from this expression, y1 is not 0. So y2, I just want to express this as carefully as so if you're following in the book. So if w has no zeros, y1 can't be 0. And y2 over y1, so this is not 0. So y2 is not a scalar multiple of y1. And the functions are linearly independent. That's really all there is to say. So this is really something that, so this is unfortunately what is called mathematics. This is trying to prove something carefully, correctly. And the theorem we did not prove is the existence and uniqueness theorem. And the theorem that we did prove is, given the existence and uniqueness theorem, that a pair of solutions to a differential equation, second order linear homogeneous differential equation, is a fundamental set of solutions if and only if the Ronskian is non-zero and if and only if the functions are linearly independent. So this is the basic fact that's proven in this section 5.1 about homogeneous equations. And that is the theoretical basis for everything that we do in this chapter. So let me solve some problems just so we see how some of this works in practice. So let me just, for example, take exercise 5.1, number 1, and number 2. Maybe number 2 is more interesting. So we have the differential equation y double prime minus 2y prime plus 2y equals 0. So here my function p of x is the constant function minus 2. My function q of x is the constant function 2. So this differential equation will have a unique solution for every initial condition everywhere on the real line. So what are two solutions of this? Well, we're given the solutions and we're just asked to check that they work. So suppose we let y1 equal e to the x cosine x. So y1 prime is e to the x cosine x minus e to the x sine x. And y1 double prime is e to the x cosine x minus e to the x sine x. That's the derivative of this, minus the derivative of this, which is e to the x sine x. So I get another one of those, minus e to the x cosine x. So these cancel, and I get minus 2 e to the x sine x. So if I calculate the left-hand side of this, what do I get? I get y double prime minus 2 e to the x sine x minus 2y prime, that's e to the x cosine x minus e to the x sine x, plus 2y plus 2 e to the x cosine x. Here I have minus 2 plus 2, they cancel. Minus 2 plus 2, that cancels. This equals 0. So this is a solution of this differential equation. And if I check the function y2 equal to e to the x sine x, this is also a solution. So each of these is a solution of this differential equation. So every linear combination of them, y equals c1 e to the x cosine x plus c2 e to the x sine x. For every choice of constants c1 and c2, this is a solution of the differential equation. But suppose now I have an initial value problem. Suppose I want to find a solution where y of 0 is 3 and y prime of 0 is -2. Let's see, so if this is y prime is c1 e to the x cosine x minus e to the x sine x plus c2, differentiate this, e to the x sine x plus e to the x cosine x. Let's see, what does that equal to? I can factor out an e to the x from everything. And then I have c1 cosine x minus sine x plus c2 sine x plus cosine x, or cosine x plus sine x. That's y prime. So I want to find C1 and C2 that satisfy the initial conditions. So from this first equation, y of 0, e to the 0 is 1. So I get y of 0 is C1 cosine 0 plus C2 sine 0. Sine 0 is 0 and cosine 0 is 1. So y of 0 is C1, so C1 has to be 3. And y prime at 0, let's see, e to the 0 is 1. I get C1 cosine 0 minus sine 0 plus C2 cosine 0 plus sine 0. Again, sine 0, 0, cosine 0 is 1. This is C1 plus C2, and that has to equal -2. But C1 is 3, so 3 plus C2 is -2, so C2 equals -5. And that's the solution of the problem. Okay, any questions about that? Let me do another problem. Let's pick something which is more interesting, where the coefficients of the differential equation are not constant. Let's say number 4. So number 4, we have the differential equation x squared minus 1 y double prime plus 4x y prime plus 2y equals 0. If we wanted to put this in standard form, divide by x squared minus 1, you get y double prime plus 4x over x squared minus 1y prime plus 2 over x squared minus 1y equals 0. And this is my function p of x. and this is my function q of x, and they're not defined at plus or minus 1, but they are continuous on the open interval from 1 to infinity, the open interval from minus infinity to minus 1, and also on the open interval from minus 1 to 1. So there are 3 open intervals on which this is a very nicely behaved, well-defined second order equation. And we're given 2 solutions. We're told that y1 equals 1 over x minus 1 and y2 equal 1 over x plus 1 are solutions. So let's check. If y1 is 1 over x minus 1, y1 prime is minus 1 over x minus 1 squared, and y1 double prime is 2 over x minus 1 cubed. So if we plug them into, let's say, the equation we started with, I have x squared minus 1 times 2 over x minus 1 cubed plus 4x times minus x minus 1 squared plus 2 over x minus 1. Let's see, what is that? I can factor out a 1 over x minus 1, and I get 2 x squared minus 1, which is x minus 1, x plus 1, over x minus 1 squared, minus 4x over x minus 1, plus 2. So that's 1 over x minus 1. See, this cancels one of these. I get 2 times x plus 1, 2x plus 2 over x minus 1, minus 4x over x minus 1, plus 2, which if I want to put this over a common denominator would be 2 times x minus 1. What is this? This is 1 over x minus 1 squared. And I have 2x plus 2 minus 4x plus 2x minus 2. And everything cancels and I get 0. So for this differential equation, 1 over x minus 1 is a solution. And if you check and do your algebra correctly, 1 over x plus 1 will also be a solution. So suppose we have the initial value problem. For the differential equation, x squared minus 1 y double prime plus 4xy prime plus 2y equals 0. We want the solution where y of 0 is minus 5, y prime of 0 is 1. So y is going to be some linear combination, c1y1 plus c2y2. That's c1 over x minus 1 and c2 over x plus 1, because y1 is 1 over x minus 1 and y2 is 1 over x plus 1. And then if I differentiate, y prime is minus c1 over x minus 1 squared minus c2 over x plus 1 squared. So y of 0 is minus c1 plus c2, and that's supposed to be minus 5. And y prime at 0 is minus c1 minus c2, right? When x is 0, these denominators are 1, minus c1 minus c2. That's supposed to equal 3. if I add these equations, I get minus 2c1 equals minus 2. So c1 equals 1, and c2 equals minus 4. So my solution satisfying the initial value problem is 1 over x minus 1 minus 4 over x plus 1. That's the solution of the initial value problem. And graph the solution. No, that's kind of hard for me. Let's see, what would the graph look like? 1 over x minus 1 looks like that. 4 over x minus 1 minus 4 over x plus 1. Let's see. Looks like that. And when you add them, yeah, looks to me kind of a mess, but they both go to 0 and it's sort of strange in the middle, but not defined at minus 1 and plus 1. But that's why this says CG, which means computer graphics, basically. Verify Obel's formula for y1 and y2. So let's verify Obel's formula. The Ronskian is y1, y2 prime minus y1 prime, y2. So y1 is 1 over x minus 1, and y2 prime is minus 1 over x plus 1 squared, minus y1 prime, which is minus 1 over x minus 1 squared, times y2, which is 1 over x plus 1. So this looks like minus 1 over x minus 1 x plus 1 squared plus 1 over x minus 1 squared x plus 1. So this is equal to 1 over x squared minus 1. So x plus 1 times x minus 1 is x squared minus 1. 1 over x minus 1 minus 1 over x plus 1. And this difference is x plus 1 minus x minus 1 is 2 over x squared minus 1 squared. Let's see if I might have done this calculation correctly. So my differential equation is y double prime plus 4x over x squared minus 1 y prime plus 2 over x squared minus 1 y equals 0. P of x is 4x over x squared minus 1. The integral from 0 to x of P of t dt is the integral from 0 to x of 4x, which is 2 times 2t over t squared minus 1 dt. This is equal to 2. So when I integrate 2t over t squared minus 1, I get the log of t squared minus 1 but it's 0, so it really should be 2 times the log 1 minus t squared. The absolute value of t squared minus 1 is 1 minus t squared. So that's the integral 0 to x p of t dt minus sign e to that. This is equal to 1 over 1 minus t squared squared. Sorry, x. Or x squared minus 1 squared. And w at 0 is equal to what? What was my Ronskian? W of 0 is equal to 2. So I get w of x is w of 0 e to the minus the integral p of t dt from 0 to x. That's 2 over x squared minus 1 squared. And by a miracle, that's exactly what we got when we calculated this directly. So this is a confirmation of Obel's formula for this problem. Okay, well, that's a little bit of work, but work is fun, I guess. So any questions about this? It does take some little bit
It's
of
just
technical
practice, but yeah, so far so good.
Yeah, but again, you have to work through everything carefully and check all the details to make sure you understand what's happening, because this is the sort of problem that you have to be able to solve in the homework and on the exams. Okay. Let's see, I do have a problem session tomorrow. I think it's set for 11 o'clock if there are any questions. If you have questions about the homework or other parts of differential equations and you can't make it at 11 o'clock tomorrow, if you send me an email, we can work out a Zoom time for you. That's always possible. Okay. Anything else? If not, we are done for the morning. We have class on Monday. The following Wednesday, there's no class. The Monday after that, there's no class. So we have one class next week on Monday, and one class the following week on Wednesday. And on Monday, I'll start to talk about section 5.2, which is the easiest case of second order differential equations, where they are linear, homogeneous, and the functions p and q are just scalars or numbers. So there's not much to understanding p and q. Okay, that's it, everyone. Be well.
You as well, Professor.
Thank you.